Welcome back. So we'll continue our discussion on vertical axis wind turbine. So what we have been talking about this different kinds of vertical axis wind turbine and their advantages and also how the operational of the vertical axis wind turbine. Primarily, we talked about two different kinds. One is the lift base, other one is the drag base. And in the lift base, we talked about this different kind of blade design of the vertical axis wind turbine, where you can, all these different design that you can see here, which we have already talked about. These are just to the purpose of these different kind of blades to have improved performance of the turbine. So sometimes we may use kind of an twisted blade, sometimes use helical kind of configuration, sometimes different configuration. Then you can have kind of a flapper, you can have pitch controlled or variable pitch foils, control turbines. And there are ways or different ways one could actually design those kind of turbine. But essentially, the idea here is that all these different strategies would lead to the different kind of um, design to. So here is another example of the frame design. The frame essentially supports the blade and deals with the statics and dynamic load. So the frame design is very important. This is a H type rotor. You can see the base frame, which is quite straightforward. Then you have a one main shaft and connecting airfoils, and then the frame. So you have two blade Darius rotor, you have three blade Darius rotor, you have Y type rotor, you have double Y type rotor. So the thing is that what you could actually do is that once you design this frame, and they can actually have this different structure to connect with the mainframe shaft and all these things. So obviously these designs are having some advantages, some disadvantages, and all their issues. But overall, vertical axis wind turbine will have its own advantages over horizontal axis wind turbine. So this is insensitive to wind direction, which is very important, and turbulence level, because your vertical axis wind turbines are smaller in size, and then you have the wind which is coming from this direction or that direction, so that can be easily handled. For that, you don't require any yaw or pitch mechanism or the extra mechanism. So, and the most important thing, since they are smaller in size, they are installed closer to the surface, and you don't have a big structure to be there. Obviously, that means there should be cheaper to build, install, and maintain. You have a very simple tower, so the blade sweeps a conical area. You have replacement and maintenance are much simpler compared to the horizontal axis wind turbine, because in horizontal axis wind turbine, your gearbox and everything sitting inside the nacelle, which is few meter above the ground level, where someone has to go up there and do the maintenance. So the maintenance become absolutely simpler or easier. Vertical axis wind turbines can be installed on horizontal axis wind turbine wind farm, and also birds and all these things. So there are certain advantages of the vertical axis wind turbine, but it is not like that everything is advantageous over horizontal axis wind turbine, but there could be some disadvantages as well. For example, one of the major drawback of the efficiency of the turbine, because the amount of power that you could extract out using horizontal axis wind turbine, you may not be able to extract out. But yes, at the same time, you can make use of this vertical axis wind turbine for the small power generation purposes. Then A well-located large horizontal axis wind turbine is continuously driven by the wind source, but that may not be possible for vertical axis wind turbine. Okay. So what you can have, so these are some of the, and then if you look at the power transmission part, so again you see this connect with the generator. This is the blades with the mainframe. Then you have a rotating shaft to gearbox to generator and electrical load, and you can see some simple power transmission system which is there. So these are the different kinds of vertical axis wind turbine that you can, vertical axis wind turbine that one can design and have advantage over that. So now what we'll talk now, since we have an good idea about this, how they look and all this. Similarly, like what we have done, so we will do some kind of a momentum simple analysis for power extraction and all these things. So so what would continue to do that, like we'll do some aerodynamics, aerodynamical or aerodynamic analysis of this vertical axis wind turbine. So that's what we are going to do. So that means what we are going to look at it is the aerodynamics of, let's say, straight blade vertical axis wind turbine. Okay. So we'll look at that and carry out the analysis the similar way. So what we'll try to look at it, we'll first look at simple single stream tube analysis. Okay, single stream tube analysis. So, and then we can also look at the multiple stream tube method. Obviously, you can have the Darius rotor can be modeled with the modification of the straight blades or so what we do in the single blade vertical axis wind turbine. So if you, let's say, the it is let's say, let us draw a circle here or maybe here. Then we will have one aerofoil. Okay, and we'll cut through this axis. This is U. This is U into 1 minus A. And this is, let's say, radius R. This is P. So this is an top view. So a single blade vertical axis wind turbine, which is seen from the top view, and this would, so it's a rotating in this direction, which is counterclockwise, and wind is seen impinging on the rotor from the left to right. So that is what it has been shown. So typically in vertical axis wind turbine, the airfoil which is being used is symmetric. Okay. So obviously the blade is oriented so that the chord line is always perpendicular to the radius of the rotation. So blade is oriented so that the chord line is perpendicular to the radius of the circle. Okay. The radius Obviously, it defines the angular position, which will normally meet the chord and makes an angle phi with the wind direction. Now, what we can draw a velocity triangle for this. Let's say if we draw this aerofoil and through which we'll pass through this line. Obviously, this is coming here, which is omega of r. This goes that way, which is u into 1 minus a. This angle is phi. Then what we have this component, we have this component, we have this component. So that's complete the triangle. This is alpha, this is omega r, u1 minus a sin phi, u1 minus a cos phi. Okay. So these are the velocity components, how it is acting on the blade. Obviously, the component due to rotation is tangential to the circle of rotation. So what we can say, the component due to rotation is tangential to the circle of rotation, and thus parallel to the chord line of the airfoil. Okay. So also one component of the wind acts tangentially, and another component of the wind is normal to the circle. So the perpendicular to the airfoil, as you can see. So induction factor, I mean A, which accounts for the deceleration of the wind as it passes through the rotor. So this we are. So now from the velocity triangle, what we write, which is very U relative square, which is essentially this is U relative omega r plus 1 minus a u sin phi square plus 1 u into 1 minus a cos phi square. That is, let's say 1. It's a simple right angle triangle formula. So this complete vector to this vector. So that's a. So this we can rewrite u rel by u is root over lambda plus 1 minus a sin phi square plus 1 minus a cos phi square. Okay, where your lambda is omega r by u, which is again tip speed ratio. So that's what you have. Second term here in the equation 2, which is becomes small. So the second term in equation 2 becomes small. So what we can write, u rel by u lambda 1 to minus a sin phi. Okay, that's what it happens. So let's say we'll say it's 3. Since the chord is perpendicular to the radius of the circle, we can find out, since the chord is perpendicular, since the chord is perpendicular to the radius of the circle, we can find alpha, which is tan inverse 1 minus a cos phi, lambda plus 1 minus a sin phi, which is 4. So at higher tip speed ratios, this second term in the denominator at higher tip speed ratio is small relative to the, so at higher lambda, this is small relative to lambda. So what happens is that, so then tan of alpha can be alpha. So what we write, alpha equals to 1 minus a cos p divided by lambda. Okay, so it's a small angle approximation. That is what we are using here. Now what we can do, we can, by analogy with momentum theory for horizontal axis wind turbine, horizontal axis rotor, let's say horizontal axis rotors, the forces on the blade can be related to the change in momentum in the airstream. So one can assume that, as before, that is far wake velocity is reduced to, so that means we can say that the far wake velocity would be u into 1 minus 2a. This is like what we have done in the horizontal, and at the rotor it will be u into 1 minus a. So what we can write, that the change in velocity is delta u, which is u into u1 minus 2a u. And the force per unit height, which is Fd, in the wind direction, one can write equals to m dot del u. So here, this is mass flow rate per unit height, mass flow rate per unit height. So what we can write, m dot this rho 2 ru 1 minus a. Okay. So r is the radius of the rotor. So r is the radius of the rotor, density of air. Then the force is Fd equals to 4r rho a 1 minus a u square. Okay. So this force must be equal to the average force on all the blades during complete revolution. So now So this is what we have found using the blade element theory by integrating around the circle and taking the number of blades into account. So what we can get by integrating um, mm, by integrating around the circle and using blade element theory, what we get b by 2 pi 0 to 2 pi 1 by half rho u rel square pod cl cos alpha plus phi d phi. So here b is number of blades, cl is lift coefficient. So this is what you have. Okay. Now what you can do uh, using this last two equation, that is equation 9 and 10. So by equating equation 9 and 10, what we get is that a into 1 minus a 1 by 8 bc by r 1 by 2 pi 0 to 2 pi u rel by u square cl cos alpha plus phi d phi. Okay, so that is number 11. Okay, so that's what you have. So now what we have is equation which this particular equation you cannot solve directly, so you need iterations. And to do this, so to solve iteratively, let y equals to lambda by 1 minus a. And then we divide both sides of equation 11 by 1 minus a square. So equation 11 divided by 1 minus a whole square. And then also you use equation 4 sine phi whole square uh, plus cos square phi sine phi d phi. So this is a little bit complicated in that sense that one could expect. Now, if you have for a given geometry, BC by R is fixed, then you can have this value of y can be assumed and 1 minus a can be calculated. And from there, the corresponding, so the corresponding lambda is y into 1 minus a. So this calculation is repeated until the desired tip speed ratio is found. So this is what you do the iteration. So once you have obtained the proper tip speed ratio, then you can do calculation for the power. So typically the power would be average torque into rotational speed. Now the torque varies with angular position. What we write P equals to omega 1 by 2 pi 0 to 2 pi Q d phi. Now torque is also the product of the, so torque is also product of tangential force into radius. Then what we have, tangential force per unit length on each blade, you have 1 by rho u rel square C into CL sin alpha CD cos alpha. Now if you assume the B number of blades, then at a rotor height of h, so if you say that rotor height is h, B is number of blades, then I have Q, which is BH capacity. Okay. Then the average rotor power we can calculate. Average rotor power over one revolution would be P omega RH BC by 2 pi half rho 0 to 2 pi UL square CL sin alpha CD cos alpha. Okay. So then we can find out the power coefficient as well, which is power divided by power in the wind passing through that area, projected area of the rotor. So the projected area of rotor would be 2RH. So then the power coefficient that you can have, power coefficient, which is Cp, that you get P by half rho 2RH U cube. So that is, so you get average power per revolution. You get what you called. So what we can write for that is that therefore what we have, this Cp lambda by 4 pi Bc by R 0 to 2 pi U rel by U square CL sin alpha 1 minus CD by CL tan alpha d phi. So that's what you have, that you get your Cp in this particular form. So you get the power per revolution and Cp. So obviously, I mean, you can see this particular integration, this can be solved numerically, but we can, so this is the analysis that we would like to establish from basic momentum theory as we have done in horizontal axis winter. We'll talk about this in more details in the next session. Thank you.